Recording is rolling. It is Thursday, October 24. I have to fill in some details about. I was looking at AP Classroom. There's one concept I haven't covered yet besides the universal gravitation we got started today. All right, so guys, when does this AP Classroom due? Yeah, finish it by Sunday night so that Monday morning we can go over the solutions. All right, so it covers the last several weeks of stuff. They crammed a bunch of stuff into Unit 2, so they reorganized that. Right. Yesterday, I was getting you guys up to speed on some things. I want to go back and look at a couple details that we did touch on yesterday, but I can show you guys a little bit better. Really, the main thing today is I want to get started on universal gravitation, which is another part of this unit, right? Because there's like a ton of content, right? Once I cover universal gravitation, it'll take me probably today and tomorrow. Then we can finally start looking at the textbook puzzles. Guys, those textbook puzzles, chapter 7 for you guys are not going to be due for probably until next Friday. So not for a while. All right, so definitely focus on the AP Classroom. That's the next thing coming. Right. Also, picture retakes tomorrow. Set 2. All right, all right. So let's look at. Oh, I've got something not on this list also. All right, here, guys. I've been grading your guys's centripetal force labs. You guys remember how you guys do the AP style write up, the whole deal? All right, guys, those write-ups, I showed you guys exactly what I was looking for, like point by point, how to get all 12 points. Right, you guys remember that? Here, I gave you guys this nice outline right here. And I think I was looking at how you guys squared yourselves out of 12. A lot of you guys gave yourselves like 10 out of 12, 11 out of 12, 12 out of 12, but you were missing a bunch of these things. Like I was looking through and you didn't say anything about like how to identify what was the independent variable or dependent variable. Like some of you guys did, but a lot of you guys didn't. So it's like, well, how do you, like, if I was following your lab procedure, how would I know, like, what changes the variable, something like that? Guys, remember to explicitly mention, right, where I have measuring equipment. Yeah, there's one place to just list the tools, but down in your procedure, make sure you say, I use the stopwatch to measure the time, right? I use the meter stick to measure the radius, right? Something like that, right? Analysis, look at your graphs. If you draw a graph as your analysis, make sure you label the axes. Guys, if you just have a graph with no axes on it and no numbers, it doesn't really mean anything, right? So it's looking for things like that. Also, conclusion. Guys, conclusion. Guys, this is a common thing. That's why I got to go over this. Conclusion. Here, this is the full master equation, right? Right. Centripetal force equals mv squared over r. You guys see this? Okay. Now, this is all 3 different labs put together. I had you guys split into 3 different experimental groups. When you put it all together, we got this. So centripetal force equals mv squared over r, right? Now, you could take any line of your data and plug in numbers and you could confirm this to be true, right? But proportion by proportion, you guys got to this force is proportional mv squared over r, right? But that came from 3 different groups. Now everybody was relating to v squared. So one, it's okay if I do this, guys, kind of cross multiply the r. Is that okay? Can I do centripetal force multiplied by r, therefore would be proportional to mv squared. Actually, you could even say equals mv squared. That's okay. You could say equals because that would also be true. Okay, is that all right? Right. Now, if I do that, what proportions was there going on? Now, everybody was relating everything to v squared. Is that true? So you could say the force was proportional to v squared. You could say the radius is proportional to v squared. Or how about mass in v squared? Wouldn't you actually divide the mass over, right? And so it'd be 1 over the mass is proportional to v squared. Okay. And if you spell that out in sentence form, it would look like this. Force is, maybe you can say directly proportional. Okay. Because proportion, like directly proportional means if you double one, the other doubles, right? To speed squared. Or the square of the speed, or how you say it, right? So that could refer to this one right here, right? Right. This one could be radius is proportional to speed squared, which looks a lot like that. You just change out force with radius, and it looks like that. Right? How about this last one? And you could go either way. Right? So it could be 1 over the mass proportional to v squared. You could do that, right? But you could swap the left and right. So maybe look at this. You could say, here, this could also be correct. Speed squared is how about this? Inversely proportional to the mass. Maybe I could say that. Inversely proportional to the mass. Or you could say directly proportional to 1 over the mass. Okay, something like that. Like if you spell it out. Because guys, I was looking at your conclusions. Some of you guys just wrote things like, "Oh, the speed is proportional." It's like speed is proportional to what? Okay, like if something's proportional to something, you need two different variables to compare, right? Right. So it's like, "Oh, speed is proportional." Wait, what? What does that even mean, right? Right. So here, just things like, "Oh, yeah, go ahead."
That it's in square, you put a root, like a square.
Okay, yeah. What if you want to do the square roots, right? Okay, yeah, that was something else I saw too, right? Because there was a bunch of that, right? Here, let me take this one. We're kind of out of paper there. So I got 1 over the mass is proportional to speed squared. Right? Could you take the square root? Do 1 over the square root like that is proportional to v. That would also be true, right? So you could say speed is, let's say, you could say directly proportional to the square root of 1 over the mass, or you could say inversely proportional. So I said the fact that I said inversely, that already takes care of the fraction 1 over, right? Right. 2, and now square root of the mass, right? It's the mass that's underneath the square root, right? Not the speed, right? So I saw some papers like that too. It was like about taking the square root of the speed. No, it's not the square root of the speed. It's the square of the speed and the mass, or the speed and the square root of the mass, however you do it. Okay? So see what's under the square root. Okay, something like that. All right, so that's a little bit cleanup from those labs. I haven't finished grading them all yet, but I'm getting through them. So getting through those. All right, so that's a little bit cleanup from there. All right, there's here, I'm gonna throw this up here. Usually I don't teach this for another few weeks, but I did see if there's at least a couple of AP classroom questions that talked about center mass and how do you guys do this. Actually, AP used to not even ask these questions at all. I would still teach it anyway, but I don't know why they threw it in this unit. Well, I can guess why. Because guys, if something's spinning, right? Like let's say I'm out in space and I like spin this pin and it starts spinning like this. Guess which point on the pin it's actually spinning about? The center mass, right? Which is the same point that it could balance on my finger if I could find the point that it could balance, right? Which could be, or if I hang it from a string. Actually, I have some foam board cutouts. I'll have you guys do this eventually, probably January. I'm thinking I have to push it off too. I have these weird shaped foam board cutouts, and you just hang them from string, and the center mass naturally hangs like straight down from the string, right? So, okay, right. But here's mathematically how you can get it. And it's very simply a weighted average. You guys see it's just a weighted average. So this is the sum of mass times position all divided by the sum of the mass, right? The little subscript I is just for, you like 1, 2, 3, 4, 5, A, B, C, D, E, whatever. But you just look at individual values. So let's do a quick example. You can just follow this right here. All right, so say I have like some, we're just looking at a one-dimensional axis. Go ahead and in your notes and sketch out a one-dimensional axis. Let's put a couple of points here, right? Maybe this is, I'll call this mass A equals about 5 kilograms. And we'll call this mass B is like 2 kilograms, maybe something like that. Okay. Now, if these were attached, let's say I stick a rod through them, right? Oh, where could this balance on my finger? Where do you think? Probably closer to the 5 kilograms or closer to the 2 kilograms? Closer to the 5 kilograms. I'm going to guess maybe about here, maybe something like that. Right? Just kind of guessing. Okay. Right. How can I find out exactly? Well, I need to introduce some numbers to say some location. Okay. Now, I can define, I don't have any numbers on here, so I can just make it whatever I want. I could put 0.0 wherever I want. Isn't that true? Right? I could put 0.0 here or here or here, here. It doesn't matter. Mathematically, I'll get the same location at the end for the center mass. Let's pick. Can be, no, here, I'll put 0.0 over here. Here could be 0.0. I'm just going to make up something, right? Right. So let's say this is like 0.1, 2, 3, it's about 4, 5, right? So it's position 1, position 2, position 3, position 4, position 5, right? On an x-axis. Maybe this is x measured in meters, right? So it's 0 meters, 1, 2, 3, 4, 5 meters, right? Variable unit. Look at that. Right? Right? You guys said. Right. So what's like the weighted average between these two mass points? Let's follow exactly this poster. That's what it says, weighted average. And then this green box is specific to, well, exactly what we're doing, right? Two masses on a one dimension axis, right? So mass times location. So I got, I'll do X bar. I can do that for like the average position. You guys see X bar? Or you could do center mass. You could put as a subscript. I need mass 1, which is 5 kilograms, times this location. I have this right at the 1 meter mark, plus the 2 kilograms is over here at the 4 meter mark. And that's all divided by the sum of the masses. 5 kilograms plus 2 kilograms. Right? You guys see that would make sense, that would work anyway, right? Because mass times position, you add all this up, you get kilogram meters. Then if you divide by the sum of masses, the mass unit kilograms goes away and you're left with meters, which could describe some position. It's just a weighted average. That's all. So look at this B. That's 5 times 1 is 5, plus 2 times 4 is 8. 8 and 5 is like 13. That's kilogram meters divided by 7 kilograms. It'd be like that, wouldn't it? Right. And then divide this out. What's 13 on 7? 1.85 x bar equals what? 1.857. I'll call that 1.86. Right, guys. 1.86. What? Can I just say 1.86 and walk away? No, 1.86 what? Meters. Right. You see that? Okay. Oh, and luckily enough, that's actually exactly where I guessed it was. Look at that. About 1.86 meters. You see that? Okay. All right, there you go. Okay. All right. Is that okay?
So how do you do it on 3 dimensions?
In 3 dimensions? Oh, okay. Yeah. How do you just send? Oh, yeah, 2 dimensions or 3 dimensions? Yeah, you could just open up more dimensions. Yeah, I think there's a. Well, here. Oh.
On the like.
Oh, yeah.
It was like on a graph on a grid. So.
Oh, okay. You just do it along each axis. So you do this for the x-axis. Yeah, guys, if you got a 2D plane, like an x-axis, y-axis, you do this for the x-axis. You get the x-coordinate like I did here. And then you say, what is it for the y-axis? So you do the exact same thing for the y-axis. So you just do it one axis at a time. Yeah.
If you're in 3D, you just do the axis also.
Yeah, and then 3D, you just do the z-axis, right? So here, if you have, here, I'll draw it out so you guys can see a little better, right? So you have, let's do 1, 2, 3, 4, 5. So here's x in meters. Let's put y in meters right here, right? So 1, 2, 3, 4, 5, something like that, right? I'll do it kind of like this. We got, suppose I have a 5 kilogram guy right here and a 2 kilogram guy right here. You got the 5 kilograms and 2 kilograms, right? Well, along the x-axis, 0, 1, 2, 3, 4, 5. That's what we just did. We just solved it. We just solved it on the x-axis because this and this are identical in terms of the x-axis. You see it? So I already know the center mass on the x-axis is like 1.86 meters.
There were three dots.
Okay. Oh, there's 3 dots? Yeah, just throw in a third one. So you just do, all you have to do is just keep repeating this process. Yeah, so if there's a third dot, just throw in mass C xc, all divided by, and then throw in mass C down here. Yeah, so you just keep doing it. Right? Okay. All right. And then let's say I want to know what is the center mass in the y direction. All I have to do is just focus on it this way. So here's 0, 1, 2, 3, 4, 5. Right? Take a weighted average along the y-axis. Right? You could do that. Okay. Right? And then if there's a, yeah, you throw in another mass, you just right, like chain that to the process. You throw, if you want a third dimension, you got have the z-axis going out of the paper. Right? You could just look along that axis. It's the weighted average. Okay. Right. Okay. Is that okay? You guys think you could do a weighted average like that? Right. Now, I do remember, because I was reading your guys' questions, make sure I could answer them all too. Actually, one of them had to do with blocks in motion, which actually would fit really nice in conservation of energy. It's really where they should have put that, or momentum I meant. That's where they should have put that question. But they have these blocks in motion. Can you guys imagine these blocks could be in motion? Right? And guys, all you do is see that X, you replace it with a V for velocity, right? And then these X's could be V's. Okay, that's all. And you just do mass times velocity, and this could be mass times velocity. Right? It's just a rate change of position. That's all it is. It's just a rate change of position. It's called velocity. Okay, you guys, make sure you guys are following me. Guys, put your phones down. Guys, why are you playing video games? Put your phones down. Phones down. You're an AP. Okay. So what did I just say? What did I just say? If the blocks are in motion, how do you change this? Yeah, just change X to V. Because it's a rate change of position. Just changes X to V, changes X to V, changes X to V. Right? And remember, guys, can velocity be positive and negative? Can you go forward and backward? Yeah, so be mindful of that too, right? And really, that's really a momentum type question, which we haven't even talked about yet, but I think you guys can figure that out. Okay, all right, guys, go with center mass. All right, let's hit a couple of things that I did talk about yesterday, but I want to go back and give you guys a cleaner version of this. So, let's look at a car on a banked road. We find car on a banked road. Here it is. Right, this car on a banked road. Right. So I did walk you guys through this. I think verbally how to derive this. Right. But later, my later classes, I like slow walked through a bunch of examples of these. I did post that video to Google Classroom yesterday. Also, I do kind of recommend you guys to look at that. Right, if you got some extra time, want to see some numerical examples of these. Right, and I did derive this. So here's how this goes. The car on the banked road. Do you guys see here? Remember, there's two. How many forces are on this car? How many forces? Two. The weight down and the normal force up to the left. Right? Now I'm going to break the normal force into components. Say, well, that normal force is holding the car up, and it's also pushing it to the left. Hence, that's the centripetal force, is the left part. Right? Actually, let's start with that left part, guys. This component right here is equal to the normal force multiplied by what? Sine or cosine of that angle. What's opposite? Sine. Right? And since it's centripetal force, I can also say mv squared over r. That's one equation. You guys see normal force times sine theta equals mv squared over r. That's one equation. Jot that down. Right? Then, how about this bit right here? Guys, is this normal force times cosine theta? And if I did it fully properly, I would say this minus this mg equals 0. But then doesn't that just mean that this is also equal to mg? Right? Yeah. And that's this right here. Normal force times cosine theta equals mg. Right? Right. So now we have a proper system of equations. Okay. Guys, if you have a system of equations, are you allowed to take one equation and divide by the other equation? Can you do that? Right. Guys, what is normal force divided by normal force? 1. Yeah, it goes away. What is sine divided by cosine? 10. Oh, yeah. And then mv squared over r divided by mg, what cancels? The m. And then it leads you exactly to that gold box. Okay. Is that maybe it's more methodical way to get there? Okay. Right. Just like that. Is that right? Right. And like I said, AP Classroom does ask you a question that has to do with a coin rolling around a funnel, but it's exactly that. That's what it is. All right. What else I got? I have to talk about this. All right. This rigid disk. All right. Yeah. Okay, it's a combination of these two right here. Right. So this was your guys' centripetal force lab. You have centripetal force, but notice it's in terms of tangential velocity, that like a linear type speed, right? That could be quantified in meters per second, right? But what if you wanted the turntable version, and you wanted it in terms of this angular velocity? Could you get that? And all you have to do is take this expression. Guys, isn't v just equal to omega times r? Right? So if you have this Roosevelt sitting here and say, how fast is it going linear speed type? Just say, well, how fast is this spinning in radians per second multiplied by its radial distance from the center? That's that right there. Just take that and substitute it right there. Can you guys do that? Okay. I have it right here. Here's your mv squared over r. Here's v equals omega r. Just substitute right there. Right, so that now that looks like this, right? So in brackets, that's what I substituted. Don't forget that's being squared, so I do have to square that. It looks like that. And then, hey, look, I got r squared on top and I got an r on bottom. Is one of those going to cancel? Yeah. Right. So it looks like that. Right. M omega squared times r. Right. You guys see that? Right. Now, that is exactly that right there. Right. So for O'Neill cylinder, if you're up in space and you get the spinning, now there's no significant real gravity around, but if you get the spinning, do you think you can walk around the outside? You feel like you're walking around on ground, maybe? Right? Something like that, right? Okay. So here's something weird I want to point out. Oh, did I point this out yesterday? I forget if I did. That in terms of tangential velocity, so this tension force, centripetal force, is proportional to 1 over r. But in terms of like a rigid disk rotating, like O'Neill cylinder, you guys see centripetal force is actually proportional to just r, right? Yeah, like the first time I saw this, I was like, wait, what? But it does make sense if you think about it deeply. But at first glance, it's kind of weird. So it's good to at least point that out. But I'm going to leave that to you guys to think about that. Okay. Right. Over r, proportional r. Right. Okay. Kind of weird. All right. Right, you guys good so far? Here, I got a question for you guys. Here, you guys do see this is hanging. It's one of my posters hanging up, right? You guys see this poster hanging up? All right, you guys ready to answer a question about that? Looks like this right here, this one. So let's say you've got an O'Neill cylinder. It's floating out in space. Oh, right. I'll give you the radius. Suppose the radius is 500 meters. You guys see a 500-meter radius? Right? It's like half a kilometer radius. Right? And let's say this is spinning, and I want to target an artificial gravity equal to Earth's gravity. Let's call it 9.8 meters per second squared today. We'll go ahead and use that full version. So these people are walking around the inside. They experience 9.8 meters per second squared. So my questions are, what is the angular velocity, omega? Like how fast does this have to be spinning to get that to happen? All right, so like we constructed the thing. We're targeting this gravity field. It's fake gravity. It's not real gravity. It's fake, right? Gonna give it a spin. How fast does it have to spin? And the follow-up question is, well, how much would it time would it take, therefore, to complete one complete revolution? Right? Now, while you guys are thinking about that, maybe you're doing some math on your paper. I'll give you guys a little bit of time. Okay, let me find, I got some demos queued up on here. Show you guys what this could kind of look like. All right, so remember you got a 500-meter radius and you're targeting 9.8 meters per second squared. All right. All right, here's from, did I mention yesterday, maybe from the 1960s, called 2001 Space Odyssey? Curious to see, how many people seen that? You guys seen that? Ooh, yeah, some of you guys have. It's fun watching movies from the 1960s. Everything's so slow-paced. It's kind of freaky. But that's what it's going to look like someday. And what does it look like on the inside? Maybe it looks kind of like this. This guy's going around. Of course, this is special effects. He's not really out in space. I think they just created a giant hamster wheel and just rolled it and had the camera fixed to one point. But yeah, it looks about like that. All right. Yeah, so running around. Okay. I should tell you guys too. Do you guys know a YouTube channel called Tom Scott? All right. He actually found one of these. He's on mute, but right. He found one of these rotating rooms. It's gonna go in there. So that's actually rotating. See how they're leaning forward? There it is from the outside, right? Okay. So you go inside. Okay. You go inside, and they're all leaning forward because they feel like they're thrown out a little bit. No, they're if you watch really carefully, they're keeping their heads really, really still because you have fluid in your inner ears that helps maintain balance. And if you start moving around inside that thing and you're not used to it, then your head goes all wackadoodle and you don't know what's going on. So you're keeping really still, right? He's trying to adjust to it. It's like moving his arms. His brain's getting used to like this weird. Everything wants to curve. At some point, they throw a tennis ball. I think they're about to throw a tennis ball here, right? And you can throw the tennis ball. He's being really careful about how he moves, right? Because he doesn't want to get dizzy and fall over. And right? Yeah, pretty much. All right. So he's going to throw the tennis ball straight, but it's going to follow a curved path because remember the tennis ball is actually moving straight. It's just the whole room that's rotating, right? That's called a Coriolis effect. All right. All right. So let's flip back over here. I think we're back over here now. All right. And all right. Who saw? Oh, whoops. I didn't flip back over. Hold on. Are we back over here? Come on. What? Hang on, timeout. Here. All right, we're back. All right, so who has by now solved for how fast this is rotating? Who knows? Who got it?
Yeah, I don't think anyone really.
It's 500 meters radius, and you're targeting 9.8 meters per second squared, and you're using this right here.
What the hell, man?
All right, here. So let's do this. All right. So no, centripetal force could be m omega squared times r. But do you think all these people walking around the inside have a different mass m? Right. But they all experience the same fake gravity field. That's really just this right here. Guys, how do you go from force to acceleration? Just divide by mass. That's Newton's second law of motion. Let's do this one here. Centripetal acceleration. Centripetal acceleration equals omega squared times r. You do that. Right. Now, you want to solve for how fast is it rotating? So you're solving for omega, right? Is that? Okay. Let's do the way I normally do with you guys. I can split my paper, can solve this in terms of numbers or in terms of variables. So in terms of variables, should I divide by r, ac over r equals omega squared, and then take the square root of both sides? Huh? Yes, yes. Yeah. Right. Right. Because isn't gravity field an acceleration type value? Right. If you drop a ball off a cliff, it's accelerating equal to the gravity field, the same acceleration. Okay. Oh, then it's the square root of centripetal acceleration divided by radius. Or I could plug the numbers in first. So here's in terms of variables. Here's in terms of numbers. 9.8 meters per second squared. It's right there. Equals omega we're solving for squared times, I gave you guys a 500 meter wide radius. It's right there. Okay. Okay. So divide over 500, that's 9.8 on 500. I got meters per second squared. I got meters is equal to omega squared. Then square root both sides. So we get what is square root of 9.8 on 500. Okay. So I'm getting omega equals 0.14 is my calculator screen number. Guys, what's the units attached to that number? Radians per second. Oh yeah, that's how fast it's rotating. Right? That could be a constant angular velocity. Right? Do that. There we go. Okay. Here's variables on the left. Here's on the right. If you plug the numbers in first, it gives you the same answer either way. Right? You guys see that? All right. Hey, I wonder how many degrees per second that would be. So I know here, omega equals 0.14 rad per second. Guys, 360 degrees is equal to how many radians? 2 pi? Pi radians? Oh, dimensional analysis railroad tracks down there. All right, you guys can still do that, right? Okay. Take my 0.14 radians, divide by, no, let me scratch that. So times 360 degrees divided by open parenthesis 2 pi radians. Okay, because I'm still seeing students that forget to open a parenthesis after they hit divide by. Guys, when you hit divide by, make sure you open parenthesis. Otherwise, you're not going to divide the 2 and the pi. Okay. All right. Got to group it together. Okay. So this is 8.0 degrees per second. Ooh, you could probably see that. Can I see a big old wheel that's rotating about 8 degrees per second? About like that. Pretty close. I guess that. All right. And there was a follow-up question. How much time would it take to complete one revolution? All right. Go ahead. Give you guys time to get caught up right there. And also solve how much time does it take? Oh, yeah, Evan?
120 on the street.
Huh?
Like, it's a turntable.
Oh, yeah. So what about that? No, it's gonna cancel out actually. Here, I can show you that one too. Let me bring that one up. All right. Yeah, I will hit that one right soon here in a minute. Okay.
But you're not done with it, sorry.
All right. Who knows? Yep.
When is the college physics?
Guys, college physics aren't due for probably until next Friday, I think. Okay. So you guys got like a whole week for this. Right. I want to give you guys some time in class to do those. In some content I haven't even covered on those yet. Like we have to start talking about universal gravitation. Right. Does anybody know how long does it take for this to make one revolution? 45 seconds? Oh yeah. All right. Think Hector got it. 45 seconds. All right. So guys, here's how fast it's spinning. 0.14 radians per second, right? Right. Okay. One revolution. Let's do some. One revolution is how many radians? 2 pi radians? 1 rev, 2 pi radians. And this is turning 0.14 radians every 1 second. How many seconds? Multiply across top, divide across the bottom. You should get 45 seconds, I think. Something like that, 45 seconds. Right. Or you could do it this way. Do you guys remember distance equals speed times time? You guys remember that? Okay. Well, the angular version of that just goes like this. Angular displacement equals angular speed times time also. So if your angular displacement was 2 pi radians and you're turning at 0.14 radians per second, you could solve for t. I mean, it works out the same 4 to 5 seconds. Right? How about degrees? How about 360 degrees? What's this turning 8 degrees every 1 second? What is that? What's 360 divided by 8? 45 seconds. Same thing. Okay. All right, guys, right there. All right, so there's a few different ways to solve that. Like if you know how fast something's turning, you just want to make one complete revolution, which is 2 pi radians, which is also 360 degrees. Yeah, you can either set up one of these equations, or you could set up some railroad tracks. They'll all lead you to the same answer. Okay. All right. I'm also getting a question about one of your textbook puzzles has to do with a turntable, a coin on a turntable, and turntable friction. Okay. So this is a lab I want to do with you guys one day, possibly next week if I can fit it in. Right, but if not, some point might be a review lab someday. Okay, but here, do you guys remember doing the turntable? You set a coin on the turntable, gave it a spin, and if you do a free body diagram, it would look like this, wouldn't it? It's got the weight down, the normal force up, and then the friction force pulls it into a circle. That act, guys, the friction force acts as a what kind of force? Centripetal. This is centripetal force, isn't it? Right, kicks off this whole process right here. The friction force is providing this centripetal force. Right. Here's your formula for friction force. Here's your formula for centripetal force on a turntable, which I just showed you guys today. All right. So I couldn't show you this poster until I showed you the O'Neill cylinder. Right, center. Right, boom, boom. Right. Now I'm saying an inequality here because I'm talking about static friction. You guys know if it's static, you could spin this a little faster, a little faster, a little faster, and that friction force builds up, builds up, builds up. That's why it's an inequality. Okay. Guys, this normal force is equal to what? The weight of the coin. Right? And then what cancels out right here? The mass, right? So if you were given this type question and you were not given the mass of the coin, or if you're given different coins with different masses, then it wouldn't even matter. Right? So this might not be in your thumbnails actually, because I think I could only fit like 16 or something. So
Is G just gravity?
yeah, G is gravity field. Okay.
The box at the bottom is just like
Yeah. This gray box is like the universal solution. So you could have any turntable spinning any angular speed, put the coin any location on it. You could have any planet. Yeah, and it'll tell you the minimum coefficient of friction to make that happen. All right. Yeah, so yeah. Do that with you guys someday. It's one of your textbook questions anyway. So got that. All right. See where we are. Okay, did that with you guys already. Did that. All right. Really, I wanted to start on universal gravitation with you guys. So let me see. I flip my screen back over here. Screen to share. Okay. Let me find. Here. I got to. But before I do gravitation, what is this? All right. I got a couple of demos from the past that I never quite got to. So let's hit those real fast. All right. You guys, he's in an elevator. Guys, he stepped in an elevator. Looks like he weighs, what, 200 pounds, something like that. All right. All right. And then, do you guys see it kicked up briefly? And then it kicked down briefly. Oh, look at that. So the elevator, so here he's probably at rest. Guys, when it kicks up, he's accelerating which way? Upward. Yeah. All right. So it's accelerating upward. So now maybe it's going from the ground floor up towards the second floor. Right. All right. Then it levels. Overshot that a little bit. Okay. Guys, when it goes back to his normal weight, is he going at constant speed? Probably constant speed. Right. Right. And then when it dips down, guys, when it dips down, does that mean he's slowing down? Mm-hmm. Yep. So he's arriving at his top floor, so he'd be accelerating down. All right. And then goes back to his usual weight. Okay. All right. So how should I get that? did I show you guys? Did I show you guys the slinky drop? Did we do this? All right, this is a good one too. Um, ah, all right. Oh, okay. I guess right at the beginning. All right, come on, drop the slinky.
Wow.
So yeah, so from the point of view, yeah, I should have shown you these guys a couple weeks ago, but we're always pressed for time. Guys, from the point of view of say like a single point near the bottom of the slinky, there's two forces on it. Guys, suppose you picked a little tiny mass point near the bottom. What are the two forces acting on it? Yeah, yeah, it's gravitational weight pulls down, right? And you got the tension pulling up. Right. And there's a time delay for that tension to dissipate, right? There's an interesting extrapolation you can make from this experiment, which is all materials have a spring-like property. Like even or even an ink pen, right? Like as I'm moving this pen around, it takes a tiny. I know this is like a very, very, very stiff spring. It takes a tiny amount of time for like the information from the bottom pen to go to the top of the pen or something like that. Because how fast can any wave travel through a material? The speed of sound. Yeah, speed of sound, right? So in this case, for a slinky, you get like a very, very tiny spring constant. So it's really visible what's going on. But yeah, this is where like if you took a pole that went from like the Earth to the moon and you swept it really fast, be like, hey, why wouldn't the end of the pole move at the speed of light or something like that? Right? Because it takes time for that wave to propagate through, right? To be like, anyway, so that's just a little bit from before. Okay.
What time should you do the second round?
Newton's second law. Okay, so if you want to do a second law application, F equals ma, you're talking about some kind of acceleration, right? Right. So you need some kind of motion. Well, I do see that the top of the slinky is in motion, so maybe we could calculate what is the acceleration, right? Actually, that could be an interesting question too. Guys, suppose at the exact same time he drops the top of the slinky, right next to it, he drops a baseball. Which one is actually moving down faster? Is the top of the slinky moving down faster? Or if he dropped a baseball next to it, would that move down faster? Who says the slinky? Who says the slinky? Who says the baseball? Right? I think it would be the slinky, and I'll tell you guys why. Because, guys, the top of the slinky has this. If you pick a single mass point, its own weight's pulling down. But what else is also pulling down? The tension. That's more forces. So now more than its own weight's pulling it down. So it's going to overall accelerate down faster. There's a second law application, right? The net force is more than the weight. The net force is the weight plus the tension from the top point of view. Okay, like that. Oh, yeah. Yeah, would this tension be the same? I think if it was negligible mass, the tension should be the same all the way through. Right, I have to think about that maybe more deeply if you consider yeah, I would tend to think it should be a common tension, I think, all the way through. Yeah, one tension pull down, one tension pull up, like that. I think so. I'm not 100% sure on that. All right. Let's see. I do have some Paul Hewitts, but you know what? My sound's not working right now. I don't know what's up with that. So here's what we do instead is I've got some posters for you guys. Let's do some posters. All right. All right. So here's quick recap from about the last week. All right. You guys remember doing this lab table? All right. We graphed all 7 of these graphs, didn't we? All right. Guys, any one of these could be a free response question on the AP exam. But we've done them all, so you know all those. There's the answer to your lab. Right. There's the rigid body version, right? If you have a turntable or a Needle cylinder, maybe you want to think more in terms of this angular velocity rather than a linear velocity, right? So you guys know both of these. Can you guys know that? You guys can also know that. Right. Okay. We got, oh, hey, there's the turntable friction. I was just walked you guys through that. So you guys seen that? All right. I will have you guys do this as a lab someday, but right, hang tight on that. I showed you guys, remember there's 3 different kind of accelerations at this point in this class. I think I went through this with you guys too, right? Right, so you guys know there's tangential acceleration in meters per second squared. There's angular acceleration in radians per second squared. Centripetal acceleration is also in meters per second squared, but it points always towards the center, right? With like centripetal force. Got that? You guys remember the conical pendulum? Guys, this could definitely be a free response question. This would be a really good free response question. Is can you draw the free body diagram? So weight down, tension force up to the left? And then can you break that tension force into components? And I have the answer right here. It's just, well, here's a system of equations you can use to solve this. Yeah. All right. So many questions you could ask about that, but this would be the beginning, right? So that free body diagram, these equations, and you could ask so many questions about that. All right. We did, guys, the vertical loop. Was this the water in the cup going around? Was this also, did we do some roller coaster questions? Do a roller coaster? It's the same math. It's the same thing, right? And if you're looking for like a minimum speed, remember this tension force or normal force, depending on the setup, could go to 0. So you could solve for the minimum value, right? Guys, be able to solve that, be able to do that. You could get asked that as a free response question. Okay. Okay. I hadn't quite shown you guys this one yet, but AP, I know, likes to ask these questions. If you have a ball on a string, and guys, here's 8 different free body diagrams for a ball on a string as it's going around. You guys see it going around a vertical loop? So it's vertically oriented. It's going up, down, up, down, up, down. Okay. Guys, is the tension always pulling directly in? Same as the direction of the string, isn't it? And the weight is always straight down. And those are always 2 forces. But do you guys see the net effect is like constantly changing, which makes it kind of weird, right? Right. Like maybe the top and the bottom is kind of easy because it's like always strictly vertical. But what about right here? Well, you could add those vectors tip to tail and say, it's off on some weird angle. Okay. Right. Now, AP also likes to ask the Ferris wheel. The Ferris wheel works a little different. Suppose you're sitting on a seat and you want to say the normal force on you compared to your weight pulling down. Now, it has to be in motion. Right? So we got vertically oriented again. But notice constant angular velocity. Now, that's different than a ball on a string. A ball on a string is probably changing speed as it's going around. It's probably speeding up on the way down and slowing down on the way up. Do you guys think the ball on a string? Unless they say otherwise. But that could be your natural assumption. But a Ferris wheel, I bet every single one of those booths is moving at the same linear speed because the whole thing's moving at a constant angular speed. Is that true? Right? So the free body diagram looks a little different. Okay. All right. I should have had you guys do this one. I should have had you guys take out a blank piece of paper so you could do this. But here, car goes over a hill and goes through a valley. Right? Now, as long as the car is in motion, here, guys, what does it feel like if you're going over a hill really fast? Zoom. Do you feel a little bit light or a little bit heavy? A little bit light. Think a little bit light, right? In fact, if you go too fast, I fly off the hill. Feel weightless. Right? So, hey, you guys see the normal force is actually less than the weight? Right? How about the bottom of the valley? The opposite would be true. You feel really heavy down there. Zooming through. The normal force up is more than the weight down. Because both of these are on a curved path. Right? If I asked you guys to identify the centripetal force, let's say this one down in the valley. Guys, for the valley, what is the centripetal force equal to? Is it normal force minus weight? Yep, normal force minus weight for the valley. How about for the hill? Let's go over to the hill. What is the centripetal force for the hill? How about the weight minus the normal force? Right? Because it'd be overall down, wouldn't it? Right? Makes sense. All right. So, okay, I'll walk you guys through this a couple of times. All right, it shows up on your AP classroom questions. So see that. All right. Man. Well, we'll get as far as we can here. I'll at least set this up. All right, so yeah, tomorrow I'll have to take you guys all day through universal gravitation. So the story historically actually starts with I'm going to go back to Kepler, who predates Isaac Newton by a few decades, I think. Right? He was making very careful astronomical. Actually, he wasn't. He got data from a guy named Tycho Brahe, I think, but he analyzed this data. So anyway, this data was accumulated over a long time. They were looking extremely precisely where are say like planets in the night sky, like where exactly is Mars night by night, right? Like tiny fraction of a degree every single moment. And Kepler was trying to figure out, well, what's like the equations that could govern the motions of these things, right? People had just figured out that the sun was at the center of the solar system. So this is after Copernicus, right? So, but okay, so what equations? And anyway, Kepler crunches this data. It comes down to like fractions of degrees to figure this out. Like where's Mars in the sky above the horizon? Oh, it's like 37.28 degrees. How did they even figure that out back in 15 whatever? I don't know, but figures out that planets follow these elliptical orbits around the sun, not actually circular, but elliptical, right? I could do an exercise with you guys, but maybe another day, right? We have you guys draw a true ellipse. He says he came up with the second law of planetary motion. It says if you look at how much time it takes, suppose it takes like a planet, I don't know, 30 days to go from here to here, and then 30 days to go from here to here. Right. Guys, when it's closer to the star, do you think it's zipping by a little bit faster? Right. And there's reasons for that. I think it'll flesh out as time goes on in this class. There's more stuff we got to talk about. Right. And as further away, it's going to go a little bit slower. Right. But you guys see that green wedge there and that green wedge there? So equal areas and equal times. So the second law of planetary motion. Now, third law of planetary motion, he was able to uncover many years later. He says the time period for a planet to go around a star squared. So for Earth, this would be 365 days. If you square that, it's directly proportional to the average distance cubed. Now, I have to say average distance because it's not true circular, but it's kind of close to circular. It's average distance cubed. Okay. He figured out that much. Now, if you combine that with Newtonian mechanics, we have to bring in Newton like many decades later and universal law of gravitation. Here's the updated modern version of the third law. It looks more like that. So anyway, all right. Dig more into that. All right, so okay, there's so much I gotta tell you guys, but we're gonna work towards this. Guys, all day tomorrow, I'm gonna tell you guys about universal gravitation. That'll take us to the weekend, and then we'll go on from there. All right, so you guys have good day. Good day.